Have you ever noticed something strange about Artemis? NASA is sending astronauts all the way back to the moon, but they are not going to land. They will travel through deep space, loop around the far side of the moon, and come home without ever touching the surface. So why would a mission this historic stop just short of landing tonight? This journey follows the real reason Artemis II must fly this way, and why that quiet decision may shape the future of human return to the moon. If this kind of calm space documentary is worth watching, please like the video, subscribe to the channel, and settle in. The mission begins far from the moon, in the wide frame of Earth and the long arc of human planning. Artemis II exists first as an idea shaped on the ground, before it becomes a flight through space. Its purpose is not to place human footsteps onto lunar soil. Its purpose is to carry a crew away from Earth, around the moon, and safely home again while proving that the spacecraft, the support systems, and the people inside them can work together beyond low Earth orbit. At this outermost level, the mission is best understood not as an attempt withheld at the last moment, but as a mission designed from the start with a different task. In this broad setting, the moon appears less as a destination for arrival than as a turning point in a larger test. Artemis II belongs to a phase of exploration in which engineers and mission planners move carefully from one verified step to the next. Spaceflight of this kind does not advance by desire alone. It advances by measured confidence. A crew can be sent only after many parts have been studied, assembled, checked, and judged ready together. The wider the distance from Earth, the more important the discipline becomes. Near Earth, a spacecraft remains in a region where help, guidance, and return options are relatively close. Beyond that region, every system must perform with greater independence. Artemis II is shaped around that reality. The mission sits within a long tradition of test flights. In human spaceflight, a test flight is not a lesser event hidden behind a more dramatic goal. It is the necessary act that makes later goals possible. A test flight places real systems into real conditions and observes how they behave. Simulations on the ground can model heat, vibration, radiation, timing, and failure cases. Uncrewed missions can prove many important things. Yet a crewed mission introduces another level of truth. Human beings consume air and water, create heat and moisture, require rest, move through the cabin, operate controls, respond to stress, and make judgments in changing conditions. A spacecraft meant for crews cannot be fully understood until a crew lives inside it during the mission it is built to support. Artemis II exists to cross that threshold. This is why the mission remains wide in its purpose, even while its path reaches deep into cislunar space. Cislunar space is the region between Earth and the Moon, including the space around both bodies. It is not the same as low Earth orbit, where many earlier human missions take place. It is farther, quieter, and less forgiving. Communication delays are still short compared with journeys to Mars, yet they are long enough to matter. Rescue is no longer immediate. Return paths must be planned more carefully. Radiation exposure differs from the environment protected in part by Earth's magnetic field. Every choice in such a mission carries more weight. Artemis II is designed to meet that environment directly, not by landing, but by proving that the crew and vehicle can move through it and come back intact. Seen from this outer level, the reason Artemis II does not land on the moon is simple. Landing is not the question the mission is built to answer. The mission asks whether the Orion spacecraft can support astronauts on a deep space journey. It asks whether launch, outbound travel, crew operations, navigation, communications, power, propulsion, re-entry, and recovery can all function together in a single human flight beyond low Earth orbit? These are large questions. They're not preliminary in the sense of being small. They're preliminary in the sense of coming before the next layer of difficulty. A lunar landing would add another entire mission within the mission-powered descent. Surface survival, ascent from the moon, and rendezvous or return architecture. Artemis II does not attempt those things because it is built to settle a prior set of unknowns first. The spacecraft itself reflects this purpose. Orion is made to carry a crew through deep space and back through Earth's atmosphere at very high speed. It is a transport and survival vehicle, not a machine that can descend to the lunar surface under its own landing system, settle onto the ground, and then rise again. Its shape, mass, protective shield, and internal arrangement all serve the needs of travel, habitation, guidance, and return. This is visible even at the program level. The mission is centered on proving the performance of the crew vehicle in the environment it must master before any later surface operation can be trusted. That broader program logic matters because lunar exploration is not one machine doing everything at once. It is a campaign made of separate but connected capabilities. One system launches, one system carries crew through space. Another system, on a later mission, is meant to support descent and ascent at the moon. Surface operations require their own planning, timelines, communications, and life support needs. Artemis II belongs to the stage where the transportation layer is tested with people on board. In that sense, the mission remains on the outside of the larger lunar enterprise. It touches the moon's neighborhood, but it does not yet move inward to the surface. There is also a practical calm in such restraint. Space agencies do not gain safety by combining every objective into one first crewed attempt. They gain safety by separating objectives so that each one can be observed clearly. When a mission carries astronauts for the first time in a new spacecraft, each major event already contains uncertainty. Launch loads must match predictions. Cabin conditions must remain stable. Software must respond properly. Electrical systems must distribute power as expected. The crew must live and work in the vehicle for days. The heat shield must protect the capsule during return through Earth's atmosphere, where the energy of re-entry from lunar distance is much greater than from low Earth orbit. Observations indicate that each of these areas can be studied in advance, yet only flight reveals the full interaction of all of them together. It remains uncertain in any new human spacecraft exactly what small deviations or unexpected patterns may appear until the mission occurs. From Earth, then, Artemis II appears as a mission defined by discipline more than by spectacle. Its meaning lies in what it chooses not to add. It does not promise a surface campaign it is not equipped to perform. It does not blur the line between deep space transport and lunar landing. Instead, it keeps its purpose broad, clear, and deliberate. It carries a crew outward from Earth to validate the foundation beneath later ambitions. In that outer frame, the moon is already central, but not yet as ground. It is part of the proving space through which the mission passes. This wide perspective also reveals a quiet truth about exploration. The most important missions are not always the ones that plant a flag or leave tracks in dust. Sometimes the decisive mission is the one that confirms that a system can carry human beings safely through a new domain. Artemis II occupies that role. It stands at the edge of Earth's familiar reach and tests whether a modern crewed spacecraft can extend that reach farther. It does not land because landing belongs to a later layer of the effort. Here, at the outermost region of purpose, the mission remains exactly what it is meant to be: a human deep space test flight whose success is measured not by touching the moon, but by making later lunar return possible. The next layer inward is not the spacecraft or the moon itself, but the structure of the campaign that places Artemis II where it belongs. A mission acquires meaning from the sequence around it. On its own, a flight around the moon might seem close to a landing, almost as if one further act were simply omitted. Within the architecture of the Artemis program, however, the distinction is far more deliberate. Artemis II is not a landing mission paused at the threshold. It is a mission assigned to a specific position in an ordered chain, and that order explains why the moon is approached but not reached as a surface destination. A campaign in space exploration is a long arrangement of tasks that cannot all be completed at once. Each task depends on confidence built by the one before it. The Artemis program follows this method. First, the launch system and spacecraft must be shown to work in a demanding flight. Then the same broad system must be shown to work with human beings aboard. Only after those steps can later missions take on the added burden of landing hardware, surface operations, and the complex joining of multiple flight elements near the moon. Artemis II occupies the middle place in this sequence. It is the first crewed mission of the program's deep space transportation system. That role is already large enough to define the mission fully. This campaign logic becomes clearer when seen against the history of human lunar exploration. During the Apollo era, several mission types were flown before a landing attempt was made. Earth orbit missions and lunar orbit missions each answered different questions. One mission tested the lunar module in Earth orbit. Another flew crew around the moon without landing. Only after those stages did a landing mission proceed. The principle remains familiar even though the hardware and the century are different. A return to the moon after many decades does not begin by repeating only the most visible achievement. It begins by rebuilding the chain of confidence from the ground up, with present-day systems, present-day standards, and present-day knowledge of risk. In the Artemis campaign, Artemis I sends Orion around the moon without a crew. That flight gathers data on launch, navigation, power, propulsion, communications, thermal control, and re-entry. Artemis II then adds the human layer. Astronauts live inside Orion, interact with its systems, and test how the spacecraft performs with crewed operations during a deep space journey. This is not a small difference. A spacecraft that succeeds without crew has not yet proven that it can sustain human life and human work under the same conditions. The campaign therefore moves one step inward, but only one. A landing remains beyond that boundary, because the campaign still requires confirmation that the crew transportation system itself is ready. This place in the sequence also protects the clarity of results. When a mission attempts too many new things at once, it becomes harder to understand any unexpected outcome. If a crewed spacecraft, a new launch system, and a lunar landing system were all introduced together in one first integrated human mission, then any anomaly would be buried within many overlapping causes. By separating the transportation test from the landing phase, the program can observe Orion and its supporting systems in a cleaner form. Engineers can study how the crewed vehicle behaves in deep space without the additional noise of descent engines, landing legs, surface timelines, and ascent operations. The architecture is therefore not only cautious, it is analytical. It creates a structure in which evidence can be gathered with greater precision. A landing mission also requires more than the simple addition of one extra vehicle. It requires a whole branch of operations that must connect smoothly with the crew vehicle. In a surface mission, the crew does not remain inside the transport craft for the entire flight. They must transfer, descend, survive on the surface, launch upward again, and rejoin the broader return plan. Each of those steps carries its own risks and technical demands. Life support must account for movement between vehicles and operation in spacesuits. Timelines must allow for delays and contingencies. Propellant margins must remain adequate in more than one vehicle. Communication and navigation must work in changing geometries near and on the lunar surface. The campaign architecture recognizes that these demands belong to a later stage because they rest on the assumption that crew transport to lunar distance has already been demonstrated. There is also an institutional rhythm in such planning. Large space programs involve many teams, many contracts, and many technologies maturing on different schedules. A launch vehicle may reach readiness on one timeline while a lunar landing system advances on another. Spacesuits, communications networks, astronaut training, mission rules, and recovery plans all progress at different speeds. The campaign architecture absorbs these differences by giving each mission a coherent purpose, even while the wider program continues to evolve. Artemis II can proceed as a crewed lunar flyby because its central requirement is Orion, and the systems needed to support that flight. A surface landing would depend on additional elements that belong to another tier of readiness. Thus, the mission's non-landing character is not a sign of incompleteness in a vague sense. It is a sign that the campaign is divided into purposeful layers. This layered design also reflects the difference between visiting lunar distance and operating at the Moon. To travel around the Moon is to enter its gravitational domain, trace a planned path, gather observations, and return. To land is to perform controlled powered descent through a precise corridor, respond to terrain and lighting, settle safely on an uneven surface, then later depart from that surface with exact timing and guidance. These are not adjacent acts in a simple sequence. They are different classes of mission. The campaign architecture respects that difference by refusing to treat them as nearly identical. Artemis II belongs to the class of missions that prove presence in deep space with crew. It does not yet belong to the class of missions that prove sustained activity at the Moon itself. Because of this, the campaign can be read almost like a narrowing funnel. At the wide end are program goals and transportation systems. Further inward come crewed validation flights. Further inward still come landing systems and surface operations. Artemis II remains in the broader part of the funnel, though it moves closer to the center than Artemis I. It narrows the unknowns. It does not remove them all. That is why its route can arc around the Moon while its purpose remains anchored in system verification. The mission does not fail to land. It remains faithful to the layer of the campaign it is designed to occupy. Seen in this light, the architecture of Artemis is not merely a schedule of missions with different names. It is a map of dependencies. One thing must be true before the next thing can responsibly be attempted. Crew transportation to lunar distance must be shown. Human performance in Orion over a multi-day deep space flight must be shown. Re-entry from lunar return speeds with a crew aboard must be shown. Only after these truths are established does it become sensible to move inward to the more concentrated demands of lunar descent and surface work. Artemis II therefore holds its place with great precision. It is close enough to the Moon to matter deeply, yet still far enough from the surface to preserve the logic of the campaign. Within this ordered structure, the mission's purpose becomes steady and unmistakable. Artemis II is the crewed proving step between an uncrewed demonstration and later landing attempts. It is positioned there by design, not by hesitation. The architecture around it gives the answer before the spacecraft ever launches. This mission will not land on the Moon because, in the sequence that makes lunar return possible, this is the mission that proves the path to the Moon can safely carry people before any path is drawn down to the surface. From the wider campaign, the mission narrows into its actual path. Here the reason Artemis II does not land on the moon becomes visible in motion itself. The planned journey is not a descent toward the surface. It is a route drawn around the moon and back to Earth, a long curved passage through space whose shape already contains the answer. The mission is built as a lunar flyby. That means the spacecraft travels outward from Earth, enters the moon's gravitational region, swings around it, and returns home. It does not settle into the kind of path from which a landing would begin. It does not carry the sequence of maneuvers required to move from travel into surface approach. Its route remains a route of passage. A route in space is not simply a line between two places. It is a balance of speed, direction, timing, and gravity. Artemis II leaves Earth aboard a powerful launch system and then continues on a carefully arranged journey that uses the pull of both Earth and the Moon. At first, this can seem close in spirit to a landing mission, because the spacecraft still goes to lunar distance and circles around the far side of the Moon. Yet the difference lies in what the path is meant to do. A landing mission must shape its motion so that the spacecraft can match the Moon more closely, reduce speed in the right way, enter the right geometry, and support further descent planning. Artemis II instead follows a return-oriented path. The Moon becomes a turning body rather than a place of arrival. This route is often described as a free return trajectory. A free return path uses gravity and initial flight design so that, if major propulsion events are completed as planned, the spacecraft can loop around the Moon and head back toward Earth without requiring a large propulsion burn near the Moon to begin the return. In simple terms, the path is shaped to come home naturally after the lunar swing. That design does not remove all risk. A mission control still monitors and corrects the flight as needed, but it gives the mission a conservative structure. It is a geometry of return. This choice reflects the mission's role as a first crewed deep space test of Orion. Safety is embedded not only in hardware and procedures, but in the path itself. The Moon, in this region of the story, is therefore not a target for contact. It is a gravitational partner in the route. Orion approaches, passes through the Moon's vicinity, bends around it, and departs again. The spacecraft may come close enough for the crew to see the surface in remarkable detail, with craters, shadows, bright highlands, and dark plains spread below. They may pass beyond the near side familiar from Earth and move into the region of the far side, where direct communication with Earth is interrupted for a time by the body of the Moon itself. All of this gives the flight emotional and scientific weight. Yet none of it changes the basic nature of the path. Looking closely at the Moon is not the same as preparing to land on it. Passing behind it is not the same as entering the operational regime of the surface. A landing mission needs a different route because landing is not a simple extension of flying close. It requires motion to be reduced and reshaped much more precisely. Spacecraft moving through deep space approach the Moon with substantial speed. To descend safely, that motion must be transformed into a controlled approach compatible with a landing system. The vehicle must be in the right place, at the right time, with the right reserve of propellant and the right alignment to begin powered descent. Artemis II does not carry that sequence in its mission design. Its close approach is part of a loop, not part of an arrival corridor. Its energy is arranged for return, not for descent. This distinction becomes even clearer when considering what Orion does after it passes the Moon. Instead of staying nearby for prolonged local operations, it continues on a path that sends it back across cislunar space toward Earth. The route forms a complete narrative of outward travel, lunar swing, and homeward fall. That homeward direction is not an afterthought. It is built into the mission from the beginning. A landing mission would treat the moon as the place where the journey changes from transit into local operation. Artemis II treats the moon as the place where the trajectory bends and the return begins. The meaning of the mission is written into that curve. There is also an operational reason for choosing such a path on a first crewed flight. A simpler mission. Geometry allows the crew and flight controllers to focus on validating core functions of deep space travel. Navigation can be tested over great distance. Communications can be observed as the spacecraft moves into changing positions relative to Earth and the Moon. Cabin life, manual operations, power use, thermal behavior, and guidance performance can all be studied within a route that remains demanding but conceptually clean. The flight still reaches beyond low Earth orbit, still exposes the crew to the deep space environment, and still carries them around the Moon. But it avoids the added complexity of converting approach into landing operations. The path itself helps preserve the mission's clarity. The free return nature of the route also carries an older logic from earlier lunar exploration. In the Apollo era, return-friendly trajectories were valued because they offered a measure of built-in resilience. Artemis II adopts that same broad principle with modern systems and modern mission planning. The spacecraft travels far from Earth, but the route is not reckless. It is disciplined. It uses celestial mechanics, the science of motion under gravity, to support crew safety. In this way, the mission's non-landing character is not merely the absence of ambition, it is the presence of a particular kind of prudence. Even the visual image of the mission can mislead if seen without this context. A crewed spacecraft arcing around the moon can appear, from a distance, almost like the threshold of a landing. The moon fills the windows. The crew nears another world. The far side passes beneath them. Earth becomes a smaller light behind. Yet in the mathematics of the route, and in the practical meaning of the mission, the threshold is elsewhere. The threshold being crossed is not the threshold of lunar touchdown. It is the threshold of crewed deep space transportation. The route proves that people can be carried outward, around the moon, and back again in Orion. That is the achievement the mission is meant to secure. So in this region, the answer comes from the trajectory itself. Artemis II will not land on the moon because its path is not a landing path. It is a flyby path, a return path, a carefully shaped loop that carries the crew into the moon's domain and then back toward Earth. Every part of that route expresses the mission's role. It approaches without arriving. It circles without descending. It turns without settling. In the quiet geometry of the flight, the purpose remains exact. The moon is not yet the ground of the mission. It is the great curve around which the mission proves that the road there can safely carry human beings and lead them home again. The route now gives way to the forces that shape it. Beyond the broad outline of the mission path lies the deeper logic of distance and energy, the quiet mathematics that determines what a spacecraft can do once it leaves Earth. Artemis II does not land on the moon partly because reaching the moon and landing there are not variations of the same act. They belong to different levels of effort. One is a passage through space across a vast interval. The other is a controlled surrender of speed at the end of that passage. When the mission is examined through the lens of energy, its limits appear calm and exact. Earth holds every departing spacecraft in a strong gravitational field. To leave that field enough to travel toward the moon, a vehicle must gain tremendous speed. That speed does not vanish once the spacecraft reaches cislunar space. It remains part of the journey, traded slowly between motion and gravity as the spacecraft climbs away from Earth, crosses the distance between worlds, and enters the moon's region. A mission to lunar distance is therefore not a gentle drift across emptiness. It is a highly energetic transition from one gravitational system into another. Artemis II is built to manage that transition with a crew on board. That alone is a demanding task. The great launch that begins the mission supplies much of the energy needed to send Orion away from Earth. After launch, the spacecraft is not simply placed on a finished path. Its motion must still be guided, monitored, and refined. Small corrections matter because even a slight deviation can grow over the length of the journey. Space is wide, and a spacecraft in flight follows the consequences of every earlier choice. The further it travels, the more important precise navigation becomes. Artemis II is therefore a mission of sustained management as much as of initial power. The crew and the flight teams observe how the spacecraft responds, how its systems perform, and how its motion remains aligned with the intended return path. In this energetic setting, the Moon is not merely far away. It is a second gravitational body that changes the character of the flight. As Orion approaches, the Moon's pull begins to matter more strongly. The spacecraft enters a region where Earth no longer shapes the motion alone. This transition is delicate and useful. A well-planned flight can use the Moon's gravity to bend its path and help direct it back toward Earth. That is one reason a flyby can be efficient and safe for a first crewed deep space mission. The energy of the journey is arranged not only to arrive near the Moon, but also to return from it without demanding a wholly new campaign of propulsion at close range. A landing changes this picture completely. To land, a spacecraft must do far more than reach the Moon. It must reduce its relative motion in a very controlled way. In orbit or on a flyby, motion around a body can continue without touching it, because there is no atmosphere at the Moon to slow a vehicle gradually. There is no broad blanket of air to create drag, no long glowing plunge through thick layers that steadily remove speed. The Moon offers almost none of that assistance. A descending spacecraft must lose speed through propulsion and guidance almost entirely by design. That means fuel, engines, control systems, landing software, and a vehicle built for descent all become essential. Artemis II does not include that extra reservoir of energy management because its mission is not to descend. The absence of atmosphere on the Moon makes this difference more severe. On Earth, returning spacecraft can use the atmosphere as part of the braking process, though that process creates great heat and must be handled with a strong shield. On the Moon, a landing craft cannot depend on air to slow down. It must carry the means to transform orbital or approach motion into a gentle arrival above a surface marked by craters, slopes, dust, and harsh contrast between light and shadow. The energy that brought the craft there must be actively removed. That operation belongs to a dedicated lander, not to Orion on Artemis II. Energy also governs what can be carried. Every added task in space requires added mass, and added mass requires added energy to launch and move. If a mission includes landing capability, it must either launch more hardware, carry more propellant, or assemble multiple pieces of the mission together in space. Each of those choices introduces complexity. More mass can affect the launch profile. More propulsion demands more storage and stricter margins. More vehicles require more coordination. Artemis II remains narrower in scope because it avoids adding that burden to a first crewed flight of Orion. The mission carries what is needed for a crewed lunar flyby and safe return. It does not stretch itself to include the heavy energetic cost of lunar descent and ascent. The return to Earth reveals the same logic from the other direction. After passing the Moon, Orion does not merely coast home in a passive sense. It comes back carrying tremendous energy gained from falling once more into Earth's gravitational well. By the time it reaches Earth's atmosphere, the spacecraft is moving far faster than vehicles returning from low Earth orbit. That speed creates intense heating during re-entry, and the heat shield must protect the crew through one of the mission's most demanding phases. This alone explains why Artemis II has a full and serious purpose without a landing. A crewed spacecraft returning from lunar distance must prove that it can survive this environment with people aboard. The mission must validate not only the outward journey, but also the violent physics of coming home. In this way, distance and energy define a kind of discipline in mission design. The moon may appear near in the sky, but in flight it remains a destination that sits across a meaningful energetic threshold. Reaching its vicinity is difficult. Returning safely is difficult. Landing adds another complete layer of difficulty that cannot be treated as a minor extension. A program that respects physics must therefore respect sequence. Artemis II accepts the scale of the first challenge and does not disguise the second as a simple extra step. There is something quiet and revealing in that restraint. The mission does not reduce ambition. It locates ambition properly within the physical world. The spacecraft must first prove that it can cross the Earth-Moon distance with crew, remain healthy and functional throughout that passage, use lunar gravity as planned, and survive the return through Earth's atmosphere. These are not partial versions of a real mission. They are real missions in themselves, defined by the deep energetic structure of travel between worlds. So the answer in this region is written in the cost of motion. Artemis II will not land on the moon because the mission is already committed to mastering another energetic task, sending humans from Earth to lunar distance and back again in a spacecraft built for transport and re-entry. Landing would require a different conversion of speed, a different vehicle, and a different store of controlled descent energy. Here, in the inner logic of distance and force, the mission remains exactly what its path has promised from the start, not a step withheld from the surface, but a deliberate proving flight across the difficult energy between Earth and the Moon. The mission now moves inward from path and force to the hardware that is not there. A lunar landing requires a machine built to land. Artemis II does not carry one. This absence is not hidden deep within technical detail. It is the most direct reason the mission will not touch the moon. However close Orion may travel, however carefully its route may bend around the lunar far side, the spacecraft remains a crew vehicle without the equipment needed to descend to the surface, settle there, and then depart again. In this region of the story, the answer becomes physical and plain. The mission cannot land because it has no lunar landing hardware. A lunar lander is not simply a stronger engine added to an existing spacecraft. It is a specialized vehicle with its own structure, propulsion, guidance, thermal control, power use, margins, and operational logic. It must be able to perform a long, controlled reduction of speed in the moon's weak gravity without atmospheric braking. It must remain stable as it approaches uneven terrain. It must manage dust disturbance near the surface. It must support the crew during the short but critical phase between spaceflight and surface contact. Then, if the mission includes return from the surface, it must support ascent as well or connect to another system that does. These are not tasks Orion is built to perform. Orion is a deep space transport capsule joined to a service module. It is not a lander in disguise. This becomes clear when considering shape and function. A crew capsule designed for high-speed return to Earth must survive a fierce passage through the atmosphere, its broad outer form, protective shield, and internal arrangement reflect that role. A lunar lander faces different demands. It does not need an Earth re-entry heat shield in the same way, but it does need descent capability, landing stability, and propulsion arranged for vertical or near-vertical control close to the surface. It must interact with the Moon at very low speed and with great precision. Orion, by contrast, is made to carry astronauts through space and then shield them during atmospheric return. Its design speaks of departure and return, not of touchdown. The mission profile confirms this hardware truth. During Artemis II, the astronauts remain in Orion for the journey. There is no separate vehicle waiting near the Moon for transfer. There is no stage of the mission in which the crew leaves the transport craft to board a descent system. There is no docked lander attached to the architecture of the flight. Without such an element, there is no practical route from flyby to surface. The mission passes through lunar space with only the systems needed for the deep space voyage itself. The hardware set defines the mission boundary. A landing architecture usually depends on division of labour among vehicles. One system may launch the crew, another may provide transfer or habitation support. A lander handles descent and ascent, or one part of that cycle. In some concepts, these systems meet in lunar orbit or near lunar space. Their interfaces must be tested. Their docking operations must be precise. Their propellant states must be known. Their power systems must remain compatible with the mission timeline. Artemis II does not include such an arrangement. It is a simpler architecture on purpose, built around Orion and its service module alone. That simplicity is not emptiness. It is the condition that allows the crew vehicle itself to be tested without the added uncertainty of a second crewed spacecraft element. There is also a mass problem hidden within any landing idea. A lander adds substantial weight, and weight in spaceflight is never merely carried along without consequence. More mass demands more launch capability, more propellant, or more assembly steps before departure. It affects guidance, mission timing, and reserve margins. For a first crewed deep space flight of Orion, attaching or coordinating a lunar lander would multiply the burden carried by the mission. It would require not just more equipment, but a more complicated plan joining different systems at lunar distance. Artemis II avoids this because its central purpose is already demanding enough. The mission needs to prove crew transport to the Moon and back. That proof would become harder to isolate if landing hardware were folded into the same first human flight. The absence of landing hardware also protects the mission from a false expectation created by distance alone. Nearness to the Moon can suggest readiness to land, but proximity is not capability. A ship at sea may approach a rocky coast, yet without a harbour craft it cannot become a vessel of landing. In a similar way, Orion can move through the Moon's vicinity without becoming a surface vehicle. The laws of motion do not care that the target looks close through a window. They care whether the spacecraft carries the engines, fuel, structure, controls, and landing design needed for the final controlled descent. Artemis II does not. A lunar surface mission also demands systems beyond the moment of arrival. Once on the Moon, astronauts would need support for surface operations, whether brief or extended. They would need spacesuits suited to lunar dust and movement in 1/6 of Earth's gravity. They would need power planning, thermal management, timelines for activity, and procedures for leaving the surface again. Even if these tasks are assigned mainly to another vehicle or later mission elements, the landing hardware must exist within that broader chain. Artemis II contains no such chain. Its hardware is complete for a flyby mission and incomplete by design for a surface mission. That incompleteness is not a flaw. It is the exact expression of mission intent. This hardware boundary also reveals how carefully exploration is staged. Engineers do not usually prove deep space crew transport and lunar landing in one leap, when the transportation system itself is flying crew for the first time. They prove the transport function first. Only after it behaves as expected with astronauts aboard does it become sensible to place that transport function in partnership with a landing system. The absence of a lander on Artemis II is therefore both a technical fact and a program decision. It keeps the mission aligned with what Orion is meant to prove. Even the language used around the mission reflects this distinction. Artemis II is described as a crewed flight around the moon. That wording is not decorative. It matches the actual hardware carried by the spacecraft stack. Orion can support the crew, navigate through deep space, communicate with Earth, maintain life support, and survive re-entry. It cannot lower itself gently onto the moon, remain there as a surface base, and then launch back upward. Those are not missing minor parts. They are entirely different functions belonging to another class of spacecraft. So in this region, the reason becomes solid and unmistakable. Artemis II will not land on the moon because no lunar lander travels with it. No descent stage waits for it, and no ascent-capable surface architecture is part of its flight. The mission carries a crew vehicle for deep space transport, not a landing vehicle for lunar contact. Everything about the hardware says the same thing. Orion is built to go out, pass by, and come home. It is not built to go down. The absence at the center of this mission is therefore not an omission made late. It is the original design boundary, clear in metal, fuel, structure, and purpose from the moment the mission is conceived. With the absent lander understood, the mission moves inward to the craft that is present. Artemis II relies on Orion as the place where the crew lives, works, and endures the journey through deep space. This region is not about what the spacecraft lacks, but about what it is meant to do. Orion is a habitation and transport system for astronauts traveling far from Earth and returning through the atmosphere at very high speed. It is not a lunar base, not a surface vehicle, and not a machine for descent. Its interior and its broader design show why the mission remains a flight around the moon rather than a landing upon it. A crew spacecraft begins with a simple requirement that soon becomes demanding. Human beings must remain alive and capable inside a small enclosed volume for many days, while the vehicle moves through vacuum, temperature extremes, and radiation beyond low Earth orbit. That means the cabin must be pressurized, the air must stay breathable, carbon dioxide must be removed, temperature and humidity must be controlled, and the arrangement of equipment must allow people to sleep, eat, monitor systems, and perform planned tasks. Orion exists to meet those conditions during a lunar distance voyage. Its success depends on keeping the crew healthy and functional in transit, not on converting itself into a landing system at the far end of the trip. The living space inside a deep space capsule is always limited. Every surface and compartment must justify its place. Equipment for guidance, displays, controls, storage, life support interfaces, safety gear, and crew provisions all compete for room. In such an environment, the spacecraft becomes a carefully arranged interior world whose purpose is continuity. The crew must be able to move enough to work effectively, but not so much that the cabin becomes inefficient. They must have access to critical controls and procedures. They must be protected from loose objects, manage daily routines, and adapt to microgravity while maintaining awareness of the mission. Orion is built around that practical reality. It is a working vessel, not a vessel of landing spectacle. This matters because a lunar landing mission asks different things of crew space. A landing mission needs not only room for transit, but integration with the tasks of surface arrival and departure. The crew may need to transfer between vehicles, prepare descent systems, don surface-ready equipment, and operate within timelines tied to landing geometry and surface conditions. Orion on Artemis II does not support such a sequence because the mission keeps the crew within one principal craft throughout the voyage. The astronauts do not approach the moon as passengers about to step into a descent cabin. They remain residents of a transport capsule whose central job is to carry them safely through deep space and back to Earth. The physical arrangement of Orion reflects this role. The capsule must shield the crew during launch, sustain them during the cruise, and then protect them during re-entry and splashdown. These demands shape everything from seat placement to storage strategy. Seats must support astronauts during periods of high acceleration. Displays and controls must remain usable in different mission phases. Supplies must be packed so that important items are available when needed without crowding the limited cabin. Waste management, meal preparation, and sleep arrangements must all be handled within a compact environment. The result is not comfort in any ordinary sense. It is a form of controlled sufficiency, where every feature supports life and work in transit. That word transit is important. Orion is made for passage. It carries the crew between worlds, but it is not intended to become the means of settling onto another world. A landing vehicle requires a different relationship between crew and craft. It must support visibility or sensing appropriate to descent, provide control authority near the surface, and often present a configuration better suited to landing stability and surface egress. Orion, by contrast, is optimized for travel and return. Its protective shell and internal systems are directed toward enduring the journey, not toward final approach to terrain. The mission, therefore, depends on Orion's ability to be a complete home for a limited time. During Artemis II, the astronauts must inhabit the spacecraft as travelers whose destination is also their route. They leave Earth, cross cislunar space, pass around the moon, and return, all within the envelope of Orion and its attached service support. This creates a closed operational world. Everything they need for survival and meaningful work during the mission must be carried, managed, or monitored through that system. The spacecraft does not open outward into surface exploration. It closes around the crew as a secure environment of passage. This role gives the mission much of its scientific and operational value. A crewed spacecraft cannot be judged only by whether it flies. It must be judged by whether people can live and function inside it under real mission conditions. How do the controls support human use over time? How does the environment feel and behave after days in deep space? How effectively can astronauts complete tasks, rest, communicate, and respond to unexpected needs within the limits of the cabin? Observations can be planned in training and approximated in ground testing, yet the lived reality of a mission reveals details that are difficult to predict fully. Artemis II exists in part to discover those details. Because Orion carries this burden, the mission does not stretch inward toward the surface. The spacecraft already has a full responsibility. It must prove itself as a deep space crew vehicle. That means its systems must remain reliable, its cabin must remain habitable, and its structure must protect the astronauts during the most severe phases of the journey. A mission that asked Orion to serve also as a lunar lander would ignore the specific integrity of its design. It would treat transport and landing as neighboring functions when they are, in fact, distinct disciplines. There is a quiet dignity in such specificity. Spacecraft become safer and more effective when their roles are clearly defined. Orion does not pretend to be every type of vehicle at once. It is the craft that carries human beings out into deep space, keeps them alive there, and brings them back through the fierce return to Earth. That is already an extraordinary set of tasks. The mission honors those tasks by allowing Orion to remain fully itself. So in this region, the answer lies within the cabin walls and the broader character of the spacecraft. Artemis II will not land on the Moon because Orion is designed as a living space for transit, not as a machine for descent and surface operation. Its volume, systems, controls, protections, and mission use all point toward one purpose: to sustain a crew on a journey around the Moon and home again. The closer the view moves to the spacecraft itself, the clearer that purpose becomes. Orion is not stopping at the Moon. It is carrying people past it, sheltering them in deep space, and returning them to Earth after proving that this new path outward can truly hold human life. Inside Orion, the most essential work is not movement through space, but the maintenance of life. The mission now turns inward from the cabin as a place to the systems that keep that place habitable. Artemis II is a crude test, not only because astronauts are present, but because the spacecraft must continuously provide the conditions that human bodies require across a journey far beyond low Earth orbit. This includes breathable air, controlled temperature, water management, carbon dioxide removal, humidity regulation, and the steady function of equipment that supports daily life. These systems are not decorative additions around the edges of the mission. They are at the center of what Artemis II is meant to prove. That is one reason the mission does not add the separate burden of a lunar landing. The basic task of sustaining life in deep space must first be shown to work with confidence. A life support system in a spacecraft is a network of machines, sensors, filters, valves, fans, storage systems, and control logic that together maintain the interior environment. The principle is simple. The cabin must remain within limits that the human body can tolerate for many days. Yet the practical challenge is constant. Crew members breathe in oxygen and breathe out carbon dioxide. They release moisture into the air. Electronics generate heat. Water is used for drinking and hygiene. Food creates packaging waste. Surfaces and airflow patterns affect where heat, droplets, and particles gather in microgravity. A deep space flight turns these ordinary processes into a closed technical problem. Artemis II is built to observe how well Orion solves that problem with astronauts aboard. On Earth, air and temperature are supported by a vast natural environment. Inside a spacecraft, that wider support disappears. Every part of the interior must be actively maintained. If air stops moving properly, pockets of carbon dioxide can collect. If cooling performance drifts, electronics and human comfort can both be affected. If humidity rises too much, condensation can appear in unwanted places. If humidity falls too low, comfort and equipment behavior can change in other ways. The cabin environment must therefore remain balanced at all times, not only for survival but for clear thinking and steady work. Artemis II does not land on the Moon because the mission already carries the responsibility of proving that this balance can be held during an actual human journey through cislunar space. Testing life support with a crew matters because human presence changes the spacecraft in ways that no uncrewed flight can fully reproduce. People move through the cabin, open and close storage, consume supplies, generate body heat, rest, exercise lightly within constraints, and respond to the environment in ways that affect system loads. They notice smells, comfort changes, awkward procedures, noise patterns, and subtle operational inconveniences. Some of these may not threaten the mission directly, but they still matter. A spacecraft intended for future exploration must be more than barely survivable. It must be workable. Crew members must be able to perform tasks without the environment slowly wearing down attention and effectiveness. Artemis II exists to reveal this lived dimension of the vehicle. This need for verification becomes stronger beyond low Earth orbit. In nearer missions, return options can be shorter and support structures more immediate. Artemis II travels far enough that the crew must rely on Orion with much greater independence. Communication with Earth continues, but the spacecraft itself must provide the real-time environment that keeps the astronauts well. That requirement gives the mission a quiet seriousness. A lunar landing would multiply the load by extending mission complexity into descent, surface exposure, and the management of more systems or vehicles. Before such expansion, the transport craft must first demonstrate that it can maintain life steadily over the outbound and return arc of a deep space mission. Water management is one part of this wider test. Water is heavy, necessary, and difficult to replace once a mission is underway. The spacecraft must carry enough for drinking and for essential needs, while also controlling where water vapor and liquid water go inside the cabin. In microgravity, water does not behave as it does on Earth. Droplets can drift, cling to surfaces, or gather where airflow carries them. Systems must prevent moisture from becoming a hazard to electronics, or a source of discomfort. The routines around water use also shape daily life for the crew. Even simple acts become part of a carefully managed environment. Artemis II helps mission planners understand how these routines function in reality. Carbon dioxide removal is another central issue. Humans cannot remain in an enclosed space unless the gas they exhale is continually reduced to safe levels. This requires reliable hardware and careful monitoring. On a deep space journey, that process must continue day after day without drift that becomes dangerous or exhausting. The crew must trust that the invisible chemistry of their cabin remains controlled. Observations from previous spacecraft and station operations provide guidance, but each vehicle has its own layout, flow patterns, equipment design, and operational rhythm. Artemis II is the mission in which Orion's own life support character is tested under true crude conditions. Temperature control also carries more importance than it may first appear. Space is not simply cold. A spacecraft alternates between sunlight and shadow. Internal heat loads change as equipment cycles on and off, and the presence of the crew adds its own warmth to the enclosed volume. Temperature must remain within ranges that protect both people and machines. Too much heat can stress systems and make work tiring. Too little can affect comfort and performance in other ways. The management of heat is therefore constant and linked to nearly every other system in the cabin. Artemis II uses the mission itself as the proving ground for how these interactions behave over time. All of this gives the flight a purpose that is complete without a landing. The mission is not waiting for its real work to begin when it nears the moon. Its real work is already underway from the moment the crew enters the spacecraft. Every hour becomes part of the test of habitability. Every ordinary act of breathing, eating, sleeping, checking displays, and moving through the cabin contributes to the evidence gathered about how Orion supports human life. That is why the mission remains focused. A first crew deep space test does not need the additional strain of a lunar descent to justify itself. It is already answering a vital question. So in this region, the reason Artemis II does not land becomes tied to the invisible systems that fill the capsule with living possibility. The mission must prove that Orion can create and sustain a stable human environment across a journey to lunar distance and back. Air, water, temperature, moisture, and waste handling must all work together without failure and without wearing down the crew. This quiet engineering is one of the true centers of the mission. Before astronauts can descend to the moon in later flights, the craft that carries them there must first show that it can keep them fully alive and capable in deep space. Artemis II is the mission that bears that responsibility, and for that reason it remains in transit. surrounding human life with tested support rather than carrying that life down to the surface. With the life support system surrounding the crew, the mission moves inward again to the people themselves and the work they perform. Artemis II is not only a test of machines, it is also a test of human operations in deep space. The astronauts are not passive passengers carried through a fixed arc around the moon. They are active participants in a demanding flight, using procedures, checking systems, interpreting information, and responding to the rhythms of the mission as it unfolds far from Earth. This human layer helps explain why Artemis II does not land on the moon. Before a crew can descend to another world, the program must first understand how that crew functions inside the new spacecraft during a real voyage beyond low Earth orbit. A crewed mission always depends on the meeting point between design and behavior. Engineers can decide where controls are placed, how displays present information, and how procedures are written. Yet once the astronauts enter the spacecraft and begin the actual mission, those plans are tested by the timing, fatigue, attention, judgment, and adaptation of real human beings. The crew must manage daily routines while also maintaining awareness of the spacecraft's condition. They monitor status information, confirm checklists, communicate with mission control, and prepare for key events. They must do these things in microgravity, within a confined volume, over a period long enough for small inefficiencies to become noticeable. Artemis II uses this reality as part of its purpose. It is the first chance to observe Orion as a working environment for astronauts in deep space, rather than as a vehicle judged mainly by engineering models and uncrewed performance. Deep space operations differ from work in low Earth orbit in ways that are subtle but important. Distance changes the emotional and practical shape of a mission. Earth is no longer close beneath the windows in the same familiar way. The spacecraft is committed to a longer arc through cislunar space, and the crew's sense of remoteness carries operational meaning. Communications remain steady, but they are part of a broader environment in which immediate return is not simple. The crew must therefore inhabit a mode of work that combines vigilance with endurance. They are proving not only that Orion can fly this path, but that people inside Orion can remain effective throughout it. This includes navigation tasks and situational awareness. A spacecraft traveling to the moon and back depends on accurate knowledge of its position, attitude, and timing. Some of this is automated, some is guided by mission control, and some depends on crew interaction with the systems on board. Astronauts must understand where the spacecraft is in its mission sequence and how to respond if a procedure requires manual input or monitoring. Even when automation performs as expected, the crew must remain ready to support the vehicle intelligently. Artemis II is therefore partly a rehearsal in the deepest sense. It trains the spacecraft and the people together under real conditions. Manual operations are an important part of this human test. A modern spacecraft can be highly automated, yet human spaceflight still values the ability of astronauts to take direct action when needed. This may involve checking guidance information, handling interfaces, confirming navigation states, or executing specific procedures during mission events. The point is not to replace automation with constant manual control. The point is to ensure that the crew can understand and use the spacecraft competently when the mission demands it. A lunar landing and a later mission would require even greater confidence in human performance, because descent and surface operations introduce more time-critical layers of judgment and coordination. Artemis II does not move to that stage because it first needs to establish the simpler but still demanding truth that astronauts can operate Orion effectively on a deep space flyby. Crew operations also include the discipline of routine. Meals, rest periods, hygiene, equipment checks, and scheduled tasks must all fit together in a confined setting, where every action affects the whole environment. In spaceflight, routine is not separate from safety. A crew that can maintain orderly habits is better able to preserve attention for critical moments. A spacecraft that supports those habits well is more likely to remain a stable working environment. Artemis II provides the first deep space opportunity to see how Orion supports that daily operational rhythm with people on board. Does the arrangement of storage help or hinder task flow? Do procedures fit naturally into the volume and sequence of the cabin? Do the astronauts remain comfortable enough to work steadily without unnecessary strain? These are mission questions, even though they are expressed through ordinary acts. Another part of the operational test is communication between crew and ground. The astronauts must report observations, receive instructions, clarify anomalies, and keep the mission state shared with controllers on Earth. This relationship is central to safe exploration. Yet it can only be understood fully when the crew is truly in deep space, carrying out the mission for which the spacecraft is designed. The practical language of flight, the timing of handovers, the clarity of procedures, and the crew's own reports about vehicle behavior all become evidence, before later missions add the concentrated demands of lunar descent and surface work. The program needs this evidence from a flight that remains focused on transport and operation in cislunar space. Human performance also includes the less visible matter of adaptation. People respond to confinement, distance, altered sleep patterns, responsibility, and the unusual visual environment of space in ways that cannot be reduced entirely to training. Astronauts are selected and prepared with care, but a real mission still reveals how mood, attention, and physical comfort interact over time. Artemis II does not need to dramatize these realities. It only needs to observe them honestly. A crude flyby around the Moon is already a rich environment for understanding how astronauts and spacecraft support one another during sustained deep space operations. This is why the mission's non-landing design remains sensible at the human level. Surface missions ask more of crews, they require transfer between vehicles, preparation for descent, surface mobility, work in lunar gravity, possible exposure to more dust-related challenges, and the mental shift from transit to local exploration and then back again. Artemis II deliberately stops short of those demands. It focuses instead on the first essential layer, whether astronauts can live and work effectively in Orion during the outward and return journey beyond low Earth orbit. So in this region, the reason Artemis II does not land on the Moon is found in the crew's own role. The mission is already a full human test of deep space operations. The astronauts must validate procedures, habitability, communication, situational awareness, manual competence, and the daily rhythm of work inside a new spacecraft on its first crewed voyage around the Moon. Before later missions move inward to the surface, this human partnership with Orion must be understood in flight. Artemis II is therefore not withholding a landing from the crew. It is giving them a different and necessary task to prove that people can carry out the work of deep space travel in Orion with steadiness, clarity, and trust. Attached to Orion, and yet outside the crew's living space, the European service module carries much of the mission's quiet strength. If the capsule is where the astronauts live, the service module is where much of the spacecraft's endurance is maintained. This region lies just beyond the cabin walls, in the machinery that provides propulsion, electrical power, thermal support, and key consumable functions during the journey. Artemis II does not land on the Moon partly because this supporting element is built to sustain travel around the Moon and back, not to become a descent engine or a surface operations platform. The more closely the mission turns toward this module, the more clearly it reveals a design devoted to passage rather than landing. A service module in spaceflight is the attached support section that carries systems the crew needs but does not inhabit directly. In Orion's case, this includes the main propulsion capability for major maneuvers, smaller thrusters for attitude control, solar arrays for electrical power, and equipment that helps support the wider environmental and systems balance of the spacecraft. The crew depends on it continuously, even while living inside the capsule ahead of it. Without this support section, Orion would not simply become less capable, it would lose the means to navigate deep space as intended. Artemis II therefore relies on a partnership between inhabited volume and external machinery. The capsule shelters the astronauts. The service module helps carry them through the mission. This arrangement already defines a limit. The service module is made to propel Orion through cislunar flight, not to lower a spacecraft onto the moon. Its engines and fuel are meant to shape the journey, maintain orientation, make planned burns, and support return. These are demanding tasks, but they are not the tasks of a dedicated lunar lander. A landing vehicle must handle a far more specialized descent regime close to the surface, where continuous control of speed and position becomes the difference between safe arrival and impact. The European service module is not configured for that role. Its propulsion system serves transport architecture, not terminal descent. The solar arrays express the same purpose in another form, spread outward like wings. They gather sunlight and convert it into electrical power for the spacecraft during the mission. This makes Orion more self-sufficient far from Earth, allowing its systems to remain active across the long outward and return arc. The arrays belong to a vehicle in transit. They are part of an energy design suited to travel through open space, where sunlight can be harvested steadily while the spacecraft moves between worlds. A surface mission would ask different questions. How is power managed during descent, surface stay, local operations, and ascent? How is equipment arranged so that landing stability and ground operations remain practical? Artemis II does not enter that domain. Its power architecture is the architecture of a flyby mission. Propulsion provides the clearest contrast. During a lunar flyby, the spacecraft needs well-planned burns at defined stages, plus fine control from smaller thrusters that maintain attitude and help manage the craft's orientation in space. Orientation matters because antennas, solar arrays, thermal surfaces, and the general stability of the vehicle all depend on it. The spacecraft must keep itself pointed properly for communication, power generation, heat management, and maneuvering. The service module is built for exactly this kind of continuous support, yet a lunar landing demands another class of propulsion behavior. Descent is not a matter of maintaining course with occasional corrections. It is a sustained and highly controlled reduction of motion near a solid surface. That is why the same support module that makes Orion capable in deep space does not make it capable of landing. The service module also helps define how the mission is integrated as a single deep space vehicle. Orion is not a simple capsule thrown outward and then left to drift. It is a multi-part spacecraft in which the capsule and service module perform distinct roles while remaining one functioning system. The astronauts interact mainly with the capsule interior, but their survival and trajectory depend on the machinery behind them. This creates a mission structure that is elegant in its clarity. One section protects human life directly, the other sustains the voyage. Neither section is intended to transform into a lunar surface craft. Together they form a transport system complete for the purpose of going around the moon and returning. There is also a programmatic reason this support function matters so much on Artemis II. A first crewed deep space test must validate not only the inhabited spacecraft, but the whole system that keeps that spacecraft viable through the mission. Engineers and mission planners need to know how propulsion performs over time, how power systems behave across the changing geometry of flight, how thrusters support attitude needs, and how the integrated vehicle responds to the actual demands of a crewed journey. The European Service Module is therefore not a background component, it is one of the core subjects of the test. That gives the mission yet another reason not to add a landing attempt. The support system itself must first prove its reliability in its intended role. Its international character also reflects the nature of the mission. The service module is provided through European partnership, tying the mission into a broader cooperative effort in exploration. This does not change the physical reason Artemis II will not land, but it does deepen the meaning of the existing architecture. The mission is already a major integration of people, nations, hardware, and operational responsibilities. It is already asking a great deal of its transportation system. A landing would require another whole vehicle layer and another whole set of operational relationships near the Moon. Artemis II stays within the coherent boundary of the system it is meant to test. Even the act of separation at the end of the mission reveals the service module's real role. Before Orion returns through Earth's atmosphere, the service module is cast off. The crew remains inside the capsule, which alone is built to survive re-entry and splashdown. This final division shows that the service module is a mission support structure rather than an all-purpose exploration machine. It helps carry the spacecraft across cislunar space, then departs before the last phase of the return. A lander would require a very different life cycle. It would remain central at the moment of lunar descent and perhaps again at ascent. The European Service Module does neither because that is not its reason for being. So in this region, the answer rests in the machinery just outside the crew's immediate world. Artemis II will not land on the Moon because the service module attached to Orion is designed to power, orient, and support a deep space transport mission, not to conduct a surface descent. Its engines guide the voyage, its solar arrays sustain the systems, its thrusters keep the spacecraft properly aligned. All of this gives Orion reach and endurance, but not landing capability. The closer the mission moves to the support structure behind the capsule, the more faithfully the design speaks. This is a spacecraft stack meant to travel around the Moon and come home again, not to lower itself into lunar dust and stand upon the surface. The journey now turns inward to the shape of safety built into the mission itself. Beyond the spacecraft, beyond the service module, beyond even the daily work of the crew, there is the deeper structure of the path home. Artemis II is arranged around a return strategy that favours resilience. This is one of the clearest reasons the mission does not land on the Moon. A landing would pull the crew away from that protective geometry and into a much narrower and more demanding set of conditions. Artemis II remains instead within a design that uses celestial motion to support the crew's return to Earth. In this region, the mission is defined not only by where it goes, but by how carefully it is able to come back. A free return trajectory is more than a route around the Moon. It is a flight path shaped so that the spacecraft, after leaving Earth and passing the Moon, naturally bends back toward Earth under the influence of gravity. The spacecraft is not without engines or corrections, and the mission is not safe by trajectory alone, yet the broad structure matters. The path contains an inherent return direction. If the spacecraft performs within expected limits, the geometry of the mission itself helps guide it home for a first crewed deep space flight of Orion. This is a powerful form of caution. It means the mission is not built around prolonged local operations near the Moon. It is built around a great loop whose deeper purpose is successful return. This idea has a quiet elegance. instead of forcing the spacecraft into a complicated and tightly constrained pattern of orbital operations near the Moon. The mission allows gravity to do part of the work. The Moon becomes not a place to stop, but a body around which the trajectory turns. This does not reduce the importance of navigation or mission control. Small corrections still matter, and the spacecraft must remain healthy and well managed throughout the flight. But the basic architecture supports a philosophy of deep space travel that values return-friendly design. Artemis II uses the Moon not as a landing site, but as the far turning point in a carefully disciplined circuit. That distinction matters because safety in human spaceflight is rarely one thing. It is not only strong metal, good software, or skilled astronauts. It is also mission geometry. A spacecraft can be made safer by the route it follows, by the number of critical events it avoids, and by the amount of flexibility it preserves. A lunar landing would replace this broad return geometry with a concentrated chain of events near the Moon. The crew would have to separate from one operational mode and enter another. Descent would need to proceed correctly. Surface timelines would need to remain stable. Ascent would later have to restore the path home. Each added event would become another point where margins shrink. Artemis II does not step into that narrower corridor. It remains within a path whose large shape is already protective. The value of a free return structure is especially strong on a first crewed mission because it reduces the dependence on perfectly executed complex operations at lunar distance. Space agencies do not remove all hazard from deep space flight. That is not possible. What they can do is arrange the mission so that fewer new hazards are introduced at once. Artemis II already asks Orion to launch with astronauts, support them in deep space, carry them around the Moon, and bring them back through high-speed re-entry. That is already a serious chain of events. By preserving a return-oriented trajectory, the mission avoids adding the wholly separate challenge of committing the crew to the lunar surface and then requiring them to climb away from it again. This safety logic also supports the gathering of evidence. A first crewed deep space mission is not only trying to succeed, it is trying to teach. Engineers and planners need a mission framework in which systems can be observed clearly and where the crew can perform meaningful work without the schedule being consumed by the extreme operational demands of a landing architecture. A free return profile creates that framework. The crew can focus on spacecraft operation, habitability, communications, navigation, and the experience of deep space flight. The mission remains ambitious, but its ambition is bounded by a path designed to preserve the possibility of safe return. That balance is one of the mission's defining strengths. There is also a psychological steadiness in such a design. Human beings travelling far from Earth do not benefit only from technical margins. They also benefit from mission structures that remain coherent and understandable. A route that carries the spacecraft out and then naturally bends it home has a certain clarity. The crew knows the mission is not trying to become too many things at once. This can support disciplined operations and a steady working environment. A landing mission, by contrast, asks the crew to move from transit into an intense local campaign near another world. That phase has its own value, but it belongs later, after the transport and return system has already earned trust. The free return concept does not mean Artemis II is simple. The spacecraft still travels enormous distance. It still moves through regions beyond low Earth orbit where rescue is not immediate and self-reliance matters. It still faces the challenge of re-entry at lunar return speeds. Safety here does not mean ease. It means design choices that keep risk within a more understandable and better bounded form. The mission honors that principle by staying with a flyby architecture. It is bold enough to test deep space human flight, but restrained enough to avoid turning the first crewed journey into a landing expedition. This restraint reveals something important about exploration strategy. In early stages of a campaign, the safest mission is not always the shortest or the nearest. Sometimes it is the mission whose geometry remains most forgiving. Artemis II accepts the long outward arc to the Moon because that is the environment Orion must prove it can handle. At the same time, it refuses the extra inward step to the surface because doing so would leave the safer broad curve of free return and replace it with the precision hazards of descent and ascent. That is not reluctance. It is structure. So in this region, the answer lies in the invisible shape of protection written into the trajectory. Artemis II will not land on the Moon because its mission is built around a return-friendly design that keeps the crew within a safer deep space loop. The Moon serves as the turning point, not the stopping point. Gravity is used not to hold the spacecraft for surface operations, but to bend it back toward Earth. This gives the mission a disciplined completeness. It proves deep space transport while preserving a broad path home. In the inward logic of mission safety, that is the right work for Artemis II to do. The crew goes to the Moon's distance, enters its realm, and then follows a path deliberately shaped to bring them back, carrying with them the knowledge needed before any later mission dares to go down. Beyond the spacecraft and its planned return path lies the environment through which the crew must travel. Artemis II now enters the region of radiation and deep space exposure, the surrounding conditions that shape human risk beyond low Earth orbit. This is another reason the mission does not land on the Moon. Before astronauts can descend to the surface in later missions, the program must first observe how a crewed Orion flight behaves in the broader space environment between Earth and the Moon. The mission must pass through that environment, measure it, endure it, and return. That outer setting is not empty. It is one of the central realities that deep space exploration must face with patience and care. Low Earth orbit remains partly sheltered by Earth's magnetic field. That field helps deflect many charged particles from the Sun and from deeper space. A spacecraft operating there is not free from radiation, but it moves within a region where Earth still offers meaningful protection. Artemis II goes beyond that region. As Orion travels toward the Moon, the crew enters a more open radiative environment. This includes exposure to galactic cosmic rays, which are highly energetic particles arriving from beyond the solar system, and to solar energetic particles, which can be released in large numbers during solar activity. These forms of radiation do not behave like ordinary weather that can simply be seen and avoided. They are invisible, intermittent, and part of the background hazard of deep space travel. Radiation matters because living tissue is sensitive to ionizing energy. Such energy can pass through the body and damage cells or genetic material. The amount of harm depends on the type of radiation, the dose, the timing, and the duration of exposure. In a short mission, risks are lower than in a much longer expedition, but they are still real and must be understood. Artemis II provides a crude opportunity to examine how Orion protects its astronauts during a mission to lunar distance. The spacecraft carries shielding as part of its structure, and mission planners can monitor the space environment, yet the actual experience of a crewed flight remains valuable evidence. That evidence is one reason the mission stays focused on flyby and return rather than adding the further demands of a landing. A landing mission would increase the environmental challenge in several ways. It could lengthen the total mission profile. It would introduce another vehicle or operational phase in which shielding conditions differ. Time on or near the lunar surface would expose astronauts within a different geometry, with local terrain below them but no atmospheric blanket above. The Moon has no global atmosphere and no strong global magnetic field to provide Earth-like protection. Surface operations therefore become part of a harsher radiative picture. Artemis II deliberately stops short of that layer. It first asks how the crew and Orion fare in transit through cislunar space, where the environmental problem is serious enough to justify the mission on its own terms. The space environment includes more than radiation alone. Thermal conditions change with orientation and sunlight. Spacecraft surfaces warm and cool depending on exposure, shadow, and internal heat loads. The crew experiences these changes through the behavior of the cabin systems that must keep conditions stable. Micrometeoroids, very small particles traveling at high speed, also exist as a background hazard. The probability of a major strike during a short mission is low, but the environment is never truly passive. Deep space places the spacecraft inside a field of ongoing physical processes that must be managed through design, monitoring, and careful mission duration. Artemis II is the mission in which Orion's interaction with these conditions is tested with people aboard. Solar activity introduces an additional layer of uncertainty. The Sun does not produce the same level of energetic output at all times. Solar storms, flares, and particle events can alter the radiation environment in ways that matter for astronauts. Mission planners track solar conditions and can assess risk. Yet the timing and strength of particular events cannot always be predicted far in advance with complete confidence. Observations indicate broad patterns tied to the solar cycle, but it remains uncertain exactly when some hazardous bursts will occur and how intense they will be by the time they reach a spacecraft. This is one reason deep space human missions are approached with caution. Artemis II must show that a modern crew vehicle and mission control framework can operate responsibly under this wider environmental uncertainty. The flight thus becomes a test of protection, awareness, and limits. Orion must do more than remain pressurized and functional. It must also provide a level of shielding and operational resilience suitable for a crew in deep space over the mission's duration. Instruments can record exposure. Procedures can help the crew respond to changing conditions. The mission itself becomes part of the learning process that informs later decisions. How much environmental margin exists? How do actual measurements compare with pre-flight models? How do crew activities, spacecraft orientation, and operational timelines interact with this background hazard? Artemis II helps answer these questions without yet adding the concentrated demands of descent and surface work. This caution is not merely technical, it reflects a broader philosophy of human exploration. Before people are asked to work on the Moon, they must first pass through the region between worlds in a spacecraft that can keep them safe enough to return. A lunar landing may be more visible, but exposure on the way there and back is part of the deeper structure of the mission. The environment between Earth and the Moon is the corridor every later surface mission must cross. If that corridor is not understood through actual crewed flight, then surface plans rest on a weaker foundation. Artemis II strengthens that foundation by making the crossing itself the subject of the mission. There is a kind of honesty in this stage of exploration. The mission does not pretend that the route to the Moon is merely a blank stretch between launch and landing. It recognizes that deep space has its own conditions, risks, and lessons. Radiation, thermal change, and exposure beyond Earth's most protective region are not side issues. They are central facts of the human journey outward. Artemis II accepts those facts and turns them into the purpose of the flight. The crew travels through the environment that later lunar explorers must also endure, and in doing so they help establish what is known and what still remains uncertain. So in this region, The reason Artemis II does not land on the Moon comes from the environment itself. The mission must first prove that astronauts can be carried through the radiative and physical conditions of cislunar space in Orion and return safely to Earth. It must gather real human experience in a region beyond low Earth orbit, where protection is reduced and uncertainty still matters. Before the program moves inward to the lunar surface, it must learn from the corridor that leads there. Artemis II therefore remains in transit, using the journey through deep space as the central test. The surrounding darkness is not empty background. It is one of the mission's true subjects, and it is enough to fill the flight with meaning long before any later mission attempts to go down to the Moon itself. The mission now moves inward to the line that stretches between spacecraft and Earth. However far Orion travels, it does not travel in isolation. Artemis II depends on continuous support from flight controllers, communication systems, tracking networks, and the disciplined exchange of information across great distance. This region is made not of metal walls or visible engines, but of signals, timing, and shared awareness. It is another reason the mission does not land on the Moon. Before astronauts can descend to the lunar surface in later flights, the program must first prove that crew, spacecraft, and Earth can remain linked and operational during a real deep space voyage around the Moon. That link is one of the mission's essential tests. Communication in deep space is more than conversation. It is the structured movement of data, commands, telemetry, voice, and timing information between Orion and the ground. Telemetry is the stream of measurements sent from the spacecraft to Earth, allowing controllers to monitor the condition of systems, crew environment, power use, guidance status, and many other details. Commands move the other way when mission control needs to adjust procedures, confirm configurations, or support the crew in specific tasks. Voice links allow astronauts and controllers to exchange updates, judgments, and responses in real time, though even in cislunar space there are small delays caused by the finite speed of light. Artemis II is designed to prove that this web of connection remains reliable across the full arc of a human mission beyond low Earth orbit. This matters because a crewed lunar flyby is not merely a matter of sending astronauts away and waiting for them to return. The spacecraft must be tracked continuously, or as continuously as geometry allows. Its path through cislunar space must be known with precision. Ground teams must understand the state of onboard systems and be able to compare real behavior with planned expectations. The crew, in turn, must be able to report what they see, ask for support, and coordinate operations. A landing mission would place even greater demands on this structure, especially near the surface where timing, local terrain, and more intense procedural sequences would narrow the margins for confusion. Artemis II does not add that extra layer. It first proves the communication and control framework needed for the transportation mission itself. The distances involved change the nature of mission support. In low Earth orbit, communication opportunities can come and go as a spacecraft moves around the planet, depending on the network in use. Yet the physical closeness of Earth still shapes the mission. Artemis II travels much farther. The signal path grows longer, and the crew's sense of separation grows with it. Even when delays remain brief by ordinary standards, they're large enough to matter operationally. A conversation in deep space does not feel exactly like one in a nearby orbital mission. Instructions and responses still flow, but the relationship between action and confirmation becomes more deliberate. This is valuable experience for all involved. It helps define how future lunar missions, and later, even more distant missions, must be conducted. Tracking is one of the quiet foundations of this system. Orion's position and motion must be known accurately enough to support navigation, communications planning, maneuver verification, and return analysis. Ground networks measure and refine the spacecraft's trajectory using radio signals and other tracking methods. These measurements help mission teams confirm whether the spacecraft is where it should be and moving as expected. The process sounds abstract, yet it is central to safe human flight. Without strong tracking and shared confidence in trajectory knowledge, a deep space mission would lose one of its main anchors of control. Artemis II makes this work visible by placing a crew inside the vehicle whose path is being measured. The voyage is therefore both a transportation test and a test of the Earth-space relationship that sustains it. Communication also has a human rhythm. Flight controllers do not merely read numbers, they interpret them within the lived flow of the mission. The crew does not merely speak in formal reports. The astronauts provide context, describe the practical feel of procedures, note subtle observations, and help the ground understand how the spacecraft behaves as a working environment. This two-way understanding is one of the great strengths of human spaceflight. It allows design knowledge and operational experience to meet in real time. Artemis II needs this kind of exchange because Orion is on its first crewed journey around the Moon. Engineers and controllers need to hear the mission as much as they need to measure it. There are also moments when communication becomes shaped by the Moon itself. As Orion moves behind the Moon relative to Earth, direct radio contact is interrupted for a period because the Moon blocks the signal path. This is not a failure. It is a known and planned feature of the geometry, yet it carries deep operational meaning. The crew and flight controllers must prepare for these intervals with care, ensuring that the spacecraft is in the expected state and that planned procedures account for temporary loss of direct contact. Such moments reveal why a lunar flyby already provides a rich test of communications and control without any need for landing operations. The mission passes through changing line-of-sight conditions, distance regimes, and support patterns that together form a full operational lesson in deep space connection. Control, in this region, does not mean remote possession of the spacecraft by the ground. It means coordinated stewardship. The crew and the flight teams share responsibility, each from their own position in the mission. Controllers monitor broad system behavior, compare performance with expected values, and support choices with the benefit of large teams and analytical resources on Earth. The crew brings immediate physical presence, direct observation, and the ability to act within the spacecraft itself. Artemis II helps define how this partnership works when Earth is no longer close. That knowledge is indispensable before later missions take astronauts into the more concentrated demands of lunar descent or surface operations. A landing would intensify all of these requirements. Communication paths would need to support more critical transitions. Tracking and navigation would need to support not just a flyby or return maneuver, but local operations around the Moon and perhaps near the surface. The coordination between spacecraft, controllers, and any additional vehicles would become more layered. Artemis II stops before that threshold, because the current mission already has a complete purpose. It is enough and necessary to prove that Orion, its crew, and the ground systems that support it can function together throughout a crewed deep space mission. There is something almost invisible yet deeply important in this. Exploration is often imagined as physical travel alone, but human exploration also depends on lines of understanding that stretch across distance. A spacecraft far from Earth remains, in a sense, joined to Earth by radio light, timing signals, procedure logic, and shared interpretation. Artemis II is one of the missions that must prove that this bond remains strong in cislunar space. Before later explorers try to stand on the Moon, the path of knowledge and support between Earth and spacecraft must itself be trusted. So in this region, the reason Artemis II does not land on the Moon lies in the communications and control framework that the mission is built to test. Orion must remain linked to Earth through telemetry, tracking, voice, command, and careful operational coordination across the full journey around the Moon and back. The crew must work with controllers through distance, delay, and temporary signal interruptions caused by geometry. These are not side tasks. They are central proof that deep space human flight can be managed responsibly. Artemis II therefore remains a mission of connection as much as travel, holding fast to the disciplined line between spacecraft and Earth, rather than extending inward to the added complexity of a lunar landing. The mission now reaches an inner layer where technical fact becomes program judgment. Artemis II is not only shaped by hardware, trajectory, and environment, it is also shaped by the slow process through which a space agency decides that a crewed system is ready to be trusted. This region is the realm of risk, caution, and certification. Here the reason the mission does not land on the Moon becomes especially clear. A first crewed deep space flight of Orion must gather evidence, reduce uncertainty, and confirm performance before any later mission adds the narrower and more dangerous demands of lunar descent. The mission remains a flyby because proving readiness is itself the central work. Risk in human spaceflight is never fully removed. It is studied, reduced, bounded, and accepted only after careful review. Every launch carries danger. Every spacecraft contains possible points of failure. Every mission unfolds inside an environment that does not forgive neglect. Certification is the process by which a vehicle, its systems, and its operations are judged acceptable for a specific purpose. This does not mean declaring the system perfect. It means deciding, on the basis of testing, analysis, inspection, and mission results, that the system can responsibly be used for the mission ahead. Artemis II is part of that process. It is not simply using certification that already exists in final form. It is helping create the evidence from which later certification decisions can be made. This is why the mission's limited scope is not a sign of uncertainty alone. It is a method for producing knowledge. A spacecraft can be tested extensively on the ground. Engineers can shake it, heat it, cool it, run software through simulations, and examine components in great detail. An uncrewed mission can then prove much more under real flight conditions. Yet a crewed mission still introduces unique realities. Human beings interact with the vehicle, consume its resources, notice details that instruments may not fully capture, and reveal the true operational character of the spacecraft. Artemis II brings Orion into that decisive stage. It asks whether the system behaves as expected with astronauts aboard during a journey round the Moon. That evidence is needed before the program can move inward to a landing mission. Certification also depends on understanding the system as a whole rather than as isolated parts. A valve may work well in testing. A display may perform well in testing. A thermal control component may perform well in testing. But once these parts are joined into a spacecraft, placed under launch stress, exposed to deep space conditions, inhabited by a crew, and brought home through high-speed re-entry, the interactions among them become the true subject. Unexpected behaviors are not always dramatic. They may appear as small procedure mismatches, sensor patterns that require reinterpretation, thermal margins that differ slightly from prediction, or crew interface issues that matter more in flight than on the ground. Artemis II exists to discover these truths while the mission is still bounded within a safer and more focused architecture than a landing expedition would require. Caution, in this setting, is a positive discipline rather than a reluctance. It means refusing to treat unknowns as if they were already solved. A lunar landing would require confidence not only in Orion, but in the combined chain of transportation, crew function, support systems, communication, surface approach, and later departure from the Moon. That level of confidence cannot responsibly be claimed until the earlier layer has been tested with people aboard. Artemis II therefore preserves a clear line between proving the crew transportation system and asking that same mission to perform a descent to another world. The caution is structural. It prevents the program from spending trust it has not yet earned. This attitude has a long place in exploration. In earlier eras of crewed lunar flight, agencies also advance by stages, allowing each mission to answer a manageable set of questions before the next one concentrated the risk further. The principle remains the same even when the spacecraft and methods change. One does not certify a system for its most difficult task by inference alone. One certifies it by moving through increasingly demanding realities, gathering evidence at each step. Artemis II fits that pattern exactly. It is demanding enough to reveal the truth about Orion in deep space, yet contained enough to preserve the mission as a test rather than a full lunar surface campaign. There is also a human dimension to certification. Astronauts must trust the spacecraft, and the organizations responsible for sending them must be able to justify that trust. Trust in this context is not emotional confidence alone. It is disciplined confidence grounded in observed performance. The crew can train for years, but true operational trust is strengthened when a system has flown as intended under real conditions. Artemis II contributes to that trust by carrying astronauts through the mission, for which Orion is presently meant to prove itself a deep space voyage around the Moon and back. Only after that can later crews be asked to depend on the same transportation system as part of a landing mission. Risk reduction also helps protect the meaning of later missions. If a first crewed Orion flight were burdened with both transportation validation and lunar landing, then any serious anomaly would cast uncertainty across too many layers at once. Was the problem rooted in deep space transport, crew procedure, landing integration, descent design, or the interaction among them? By keeping Artemis II focused, the program allows the evidence to remain clearer. The mission can succeed or reveal problems in a form that better informs the next step. In this way, caution becomes efficient. It does not slow knowledge, it organizes knowledge. Certification after Artemis II will still not make future missions simple. It will only make them better grounded. Some uncertainties may be reduced. Others may be newly discovered. Observations may confirm models in many areas while challenging them in others. That is the normal and necessary pattern of exploration. Artemis II is valuable precisely because it offers the chance for reality to speak before the program commits crews to even more complex operations. A lunar landing belongs after this conversation with reality, not before it. So in this region, the reason Artemis II does not land on the Moon is found in the logic of responsible proof. The mission must serve as a certification step, gathering real evidence about Orion, its systems, its crew operations, and its performance in deep space before later missions add the concentrated risk of descent and surface work. Risk is not denied, it is managed through sequence. Caution is not timidity. It is the means by which a crewed program becomes worthy of trust. Artemis II therefore remains where it should remain at the stage where a new deep space transportation system earns its authority through flight, so that later missions may move closer to the Moon with stronger knowledge beneath them. The mission now approaches its most concentrated explanation. All the earlier layers begin to gather here: the campaign sequence, the flyby route, The energy of travel, the absence of landing hardware, the role of Orion, the work of life support, the crew's operations, the service module, the free return design, the deep space environment, the communication link to Earth, and the discipline of certification. In this region, these separate truths are no longer examined one by one. They combine into a single answer. Artemis II does not land on the Moon because every major feature of the mission points toward another purpose. The mission is not almost a landing. It is a deliberately bounded step that prepares the conditions under which a later landing can responsibly occur. A lunar landing is often imagined as the natural climax of any crewed journey to the Moon. That image is powerful because the surface is visible, solid, and symbolically complete. A spacecraft circling or passing the Moon can look, from a distance, like a mission that stops just short of its obvious conclusion. Yet this impression fades when the mission is viewed in technical and operational detail. Artemis II does not stop short of its goal. It reaches its actual goal by not attempting the wrong one. Its design shows this with unusual consistency. The route is built for passage and return. The spacecraft is built for transit and re-entry. The support module is built for endurance in deep space. The mission rules are built around proof, safety, and evidence. There is no hidden landing waiting inside this structure. There is only a clear boundary that later missions are meant to cross after this one has done its work. That later stage depends on several things Artemis II does not carry. A landing mission requires a vehicle able to descend through vacuum by propulsion alone, settle onto uneven lunar terrain, support the crew at the surface, and then either ascend again or integrate with the larger return architecture. It also requires operational confidence that human beings can travel to lunar distance and back in Orion without exposing later surface missions to untested weaknesses in the transport layer. This is why landing comes later not by delay alone but by logic. Surface operations rest on transportation truth. They rest on life support truth. They rest on communication truth, navigation truth, and environmental truth. Artemis II is the mission that seeks those truths in flight. This combined logic can be imagined as a narrowing of unknowns. Before Artemis II, some questions can be answered only by analysis, testing, and uncrewed flight. After Artemis II, at least some of those questions should be answered by lived human experience in deep space. Can Orion sustain astronauts across the full journey around the Moon and back? Can the crew work effectively within the spacecraft? Can the integrated system perform its deep space role with the steadiness that later missions require? If the answer is yes in enough critical areas, then a landing mission stands on stronger ground. If the answer reveals problems, then the program has learned those problems before placing astronauts into a more concentrated and less forgiving surface campaign. Either outcome justifies the mission's existence. Both outcomes show why Artemis II should not also have been asked to land. There is also a deeper strategic reason for this sequence. Space exploration becomes sustainable only when each mission contributes clearly to the readiness of the next. A mission that tries to do too much may produce spectacle, but it can weaken the chain of understanding that future missions depend on. Artemis II instead strengthens that chain. It is focused enough to isolate the role of Orion as a crewed deep space transport system. It is demanding enough to expose the spacecraft and the crew to the real environment between Earth and the Moon. It is conservative enough to protect the return through a broad safety geometry. These traits together make the mission useful in the fullest sense. It advances the program by clarifying what is known before the program asks for more. Why landing comes later can also be understood through the idea of operational layers. The first layer is launch and departure from Earth. The next layer is transport through cislunar space. The next is survival and work in that environment. After that come the operations specific to the Moon as a place of local activity descent, surface procedures, ascent, and whatever rendezvous or transfer architecture supports return. Artemis II occupies the earlier set of layers. It does not fail to reach the later ones. It remains where it is most valuable. Its closeness to the Moon makes this easier to misunderstand, because the mission physically approaches the world that it does not touch. But physical approach is not the same as operational readiness. One can enter the neighborhood of a place without yet possessing the means to live and work there. The mission therefore acts as a gate rather than a shortcut. It does not provide the Moon's surface directly. It opens the path toward missions that may. This role may seem less dramatic than a landing, but in the structure of a long exploration program it is often more decisive. Later crews who do descend to the Moon depend on the evidence carried home by Artemis II. They depend on lessons about Orion's performance, crew procedures, environmental exposure, and the practical reality of deep space flight in a modern system. In this sense, the mission's refusal to land is what gives it meaning. By not reaching for a surface campaign too early, it creates the basis for surface missions that are more credible and more responsible. There is no contradiction in this. The mission goes to the Moon so that it does not have to land there yet. It travels far enough to test the real conditions of lunar distance flight. It stops short of the surface so that the findings remain focused on transport, support, and return. This is not a partial commitment to lunar exploration. It is a disciplined commitment to the part of lunar exploration that must be trusted first. The answer becomes especially clear here because all the earlier reasons reinforce one another rather than competing. The missing lander, the chosen trajectory, the role of Orion, the support of the service module, the free return safety structure, the space environment, and the need for certification all converge on the same conclusion. So in this region, why landing comes later is no longer a matter of any single technical limitation. It is the combined logic of the entire mission. Artemis II will not land on the Moon because it is the step that proves the transport system, the crewed operation, the environmental resilience, and the return architecture that later surface missions require. To land later, the program must first fly this mission now. The Moon's surface remains beyond the boundary not because the mission falls short, but because the mission holds its shape. It stays faithful to the layer of exploration it is meant to complete, and by doing so, it makes the inward step to the surface more real for the missions that follow. At the innermost level, the mission is no longer defined only by hardware, procedure, or flight path. It becomes a statement about what kind of exploration is being attempted and what it means to move carefully toward another world. Artemis II does not land on the Moon because its deepest purpose is not to claim the surface, but to restore a human path outward in a form that can be trusted. This inner meaning is quieter than the image of boots on dust. It is less visible, less immediate, and yet in some ways more fundamental. Before a civilization can return people to the Moon as visitors who work there, it must first prove that it can once again carry people safely through the space between Earth and the Moon in a modern spacecraft built for that journey. Artemis II is that proof in human form. The mission carries a crew, and that fact changes its meaning. Human beings do not merely ride inside the spacecraft as symbolic passengers. Their presence turns the flight into a measure of confidence. A machine sent around the Moon without people can demonstrate engineering performance. A machine sent around the Moon with people must also demonstrate responsibility. It must show that the systems built on Earth can protect breath, thought, judgment, and life across a region of space where Earth is distant enough to matter. That is why Artemis II remains so carefully bounded. The mission is not trying to make the moon familiar too quickly. It is trying to make the path to the moon real again. At this inward level, not landing becomes part of the mission's honesty. A landing is one of the clearest symbols in exploration. It leaves marks. It creates a visible instant of arrival. Yet symbols can mislead if they are reached before the underlying structure is ready. Artemis II resists that temptation. It accepts that the surface is not the only truth that matters. The journey itself must become trustworthy. The crew vehicle must become a place in which human life can cross deep space with steadiness. The operational partnership with Earth must become reliable. The mission must turn uncertainty into knowledge by refusing to treat the moon as a destination that must always end in touchdown. Artemis II restores the value of transit, of preparation, and of measured return. There is also a human continuity within this restraint. The flight reconnects present-day astronauts with a realm that earlier generations once entered, but it does so under modern conditions, with different hardware, different standards, and a different understanding of long-term exploration. The mission is not simply repeating history, it is rebuilding capability. Rebuilding is inward work. It does not always look dramatic from a distance because much of its meaning lies in what becomes possible afterward. A bridge matters not only when it is crossed once, but when it stands ready to carry many crossings. Artemis II has something of that character. It is a mission meant to strengthen a route, not merely to complete an isolated gesture. The moon, in this inner view, becomes both near and withheld. The crew travels to its distance, sees it closely, passes around it, and comes home without touching it. That absence of touchdown might seem incomplete only if exploration is judged by contact alone. But there is another way to understand nearness. To travel safely through the moon's domain in a spacecraft intended for future expeditions is already to change the human relationship with that world. The mission makes the moon operationally present again in the life of human spaceflight. It turns the lunar distance from an abstract ambition into a working environment once more. That change matters deeply, even without a landing. The crew themselves embody this meaning. They represent not conquest but rehearsal in the highest sense of the word. Their work is serious because it is in service of later crews, later missions, and later risks not yet taken. They carry the responsibility of first proof. In many areas of exploration, the first proof is less celebrated than the later visible achievement. Yet the first proof is often the more delicate task. It must reveal truth without the protection of precedent in the exact system being used. Artemis, 2 places that burden on a human flight around the moon, and the crew's value lies precisely in meeting that burden rather than in stepping onto the surface before the transportation system has fully earned such a step. This gives the mission a certain humility, though not a small one. It does not announce that human presence at the moon is fulfilled by approach alone. It does something more disciplined. It says that approach must first be mastered honestly. It says that the road to the moon is itself a frontier that deserves attention. It says that carrying people out and back through deep space in a new craft is not a lesser achievement waiting for a greater one to replace it. It is the inner act by which a program proves that its outward dreams rest on something more substantial than desire. There is a broader meaning as well. Human exploration becomes durable when it learns how to move outward without mistaking spectacle for readiness. A program that can separate its steps wisely is a program more likely to endure. Artemis II shows that kind of maturity. It accepts a mission whose success will be measured by knowledge, resilience, and return rather than by surface contact. In doing so, It treats the astronauts not as symbols to be displayed at the farthest visible point, but as participants in a careful expansion of reach. That may be the most important inward truth of all. The mission honors human life not by asking it to do everything at once, but by asking it to prove one essential thing well. So at the center of the subject, the answer is not mechanical, though mechanics support it. Artemis II will not land on the moon because the mission's deepest purpose is to restore confidence in human deep space travel before the next, more concentrated form of lunar exploration begins. It is a mission about trust made visible in motion, trust in the spacecraft, trust in the crew, trust in the partnership between Earth and the vehicle travelling far beyond it. Trust earned not through symbol alone, but through the full arc of departure, passage, endurance, and return. In this final inward sense, the mission does exactly what it is meant to do. It approaches the moon closely enough to make the path real, and stops short of the surface so that reality can be understood before ambition goes further. That is why Artemis II does not land. Its true destination is not the lunar ground, but the restoration of a human capability that later missions will carry the rest of the way. The journey comes to rest in the simple shape it has held from the beginning. Artemis II travels outward from Earth, enters the moon's realm, curves around it, and returns without landing because landing is not the truth this mission is built to test. The flight asks something quieter and more essential. It asks whether a modern crewed spacecraft can carry human beings through deep space, sustain them there, keep them connected to Earth, and bring them safely home again. Everything in the mission serves that purpose. The route, the vehicle, the support systems, the crew's work, and the careful return all remain faithful to that one task. In that sense, the mission is not defined by what it refuses, but by what it restores. It restores a human path beyond low Earth orbit. It restores the lived reality of travelling to lunar distance. It restores the discipline of proving one layer of exploration before moving inward to the next. The moon remains close, visible, and untouching, not as a denial, but as a boundary respected for now. Beyond that boundary lie later missions, later vehicles, and later decisions that must stand on the knowledge carried home by this one. There is calm in such a design. The astronauts do not need to land in order for the mission to matter fully. Their passage around the moon is already enough to test the road that future crews must travel. Their return is already enough to show whether Orion can become a trusted bridge between Earth and lunar space. If that bridge holds, then later missions may cross it further. If it reveals weakness, then wisdom has arrived before greater risk. So the mission ends where its meaning has always lived, not on the moon's surface, but in the careful proving of a path. Artemis II goes far enough to make the future real, and returns soon enough to make that future safer.